2 slides back, we said that we're going to be looking for eigenvectors because those eigenvectors seem to be pointing along the dimension of the greatest variance. Right? And that was a visual observation. So now let's actually prove it. Let's prove that those are pointing in the right direction. So what I'm going to say is let's directly look for a dimension where the projections are as varied as possible. So I have a bunch of data points, x1, x2, x3. I'm going to look for the vector E such that when I project those x's to this vector E, the spread of the points, so these points where they that correspond to the projections, to the dot products, I want the spread of these points to be as high as possible. And it's not actually too complicated, right? So what is the variance of these projections, right? So suppose I have a certain vector E. What is the variance along that vector E? Well, the variance is really pretty simple, right? For each instance, I'm going to take some number, subtract the mean of those numbers, square it, add it up, divide by n. That's the variance. And what are those numbers? Those numbers are where the dotted line falls onto my dimension. They're defined by the dot product between each of the instances xi in the original space and that dimension E. So it's just the dot product between xi and E. Right? It's the sum of xij times ej summed up over all attributes j from 1 to d. Okay? Now, I'm going to assume that that mean is 0. And on the next slide, we're actually going to prove why it is, but on this slide, there's not going to be space. So for now, just believe me when I say that that mu is going to be 0. Okay? So the variance is really just going to be that quantity over there. Okay? Now, if I'm directly looking for the dimension of the greatest variance, and I don't know anything about linear algebra and eigenvectors and eigenvalues, I can just say, well, that's an objective function. I know how to minimize and maximize objective functions, right? I'm looking for the vector E that makes this quantity as big as possible. So that quantity, the variance, I want to make it as big as possible. Now, it turns out that I can't quite work with that quantity by itself because there's a way to cheat. Right? I can come up with a vector right now without even looking at any data that's going to give me the highest possible variance of the data. So, any guess how you can do that?
Just put E as like the highest value possible.
Yeah. So if I take those EJs and stick huge numbers there, like, positive gazillion for every attribute, where gazillion is bigger than anything that you come up with, right? So that vector is certainly going to have the highest possible variance because all of those dot products are going to be huge. You're multiplying numbers by huge numbers. Okay, so that's not nice. I don't really care about that. So I want to put a cap on that. And one way to put a cap on that is to say, okay, yes, I want the vector where the variance is going to be the biggest, but I'm also going to put a cap on the size of that vector. I'm going to make it unit length. Right? So if I keep it unit length, then it's going to have to get turned to maximize the variance. So I want to maximize the variance subject to it being unit length. And this is constrained optimization. So what you have to do is you have to add Lagrange multiplier, right? So the way you do it is you take your constraint. I want the length of my vector to be 1. So the length of my vector is just the sum of the squares of its components. So I want that to be equal to 1, so I take the actual sum, subtract 1, multiply it by lambda. That's my Lagrange multiplier. So now I have a constrained objective function. Now, if I maximize that, then I'm going to end up with the right vector for some value lambda. So how do I maximize things? Well, you take the derivative and then see where that derivative is 0. So the derivative in this case happens to look like that, right? I'm differentiating the variance with respect to components of my vector E. Remember, my vector E, that's the blue line, it has certain coordinates So A is just one of the attributes. It's one of the elements in that vector. So if I differentiate the variance with respect to any one of the attributes, if my vector E happens to be the best vector, the one that gives me the highest variance, then that derivative has to be 0, right, by definition. Because at the maximum or the minimum, the derivative must be 0. Right, so what is the derivative with respect to the 8th attribute? So I have something squared here, so 2 comes out, it becomes 1. I still have the same summation in the parentheses, and then once I differentiate inside the sum, I'm differentiating with respect to EA, so one of these EJs is going to be EA, and the corresponding XIJ, which is really XIA, is going to come out. Okay, so that's the derivative of the first part, and the derivative of the second part is even simpler, right? The sum, only one element of it matters, only the element where, by the way, I guess that has to be J, where that J is equal to A, so I take the square of it, differentiate, so I get 2EA times lambda. Right. So that is the derivative, and if my vector E is the optimal vector, then that derivative must be 0, and it must be 0 for every single attribute A. Right. So along every attribute value, the derivative is 0, then you know that you have optimized, you found the optimal vector. Now let's take this, and let's play around with this just a little bit. What I'm going to do is I'm going to take this 2 lambda EA, move it on the other side, and then I'm going to change the order of summations. I can always move summations outside. Right? So I take this the sum over j's, so this is the sum that goes over attributes, and I move it to the very outside, and I take the EJ component with it because it doesn't depend on I, and what I leave inside is the sum over i's. I's are the different instances in my data, the different data points. So the x1, x2, x3, those are the i's. And what I have left there is xia times xij, and I also have 1 over n from here that I'm pulling in there. Now you look at this formula, you stare at it for a very, very long time, and you start to have this tingling feeling like you've seen it somewhere before, right? We've seen it a couple slides back. This is the covariance. Remember, we normalize the data out, so the mean of attribute A is 0 and the mean of attribute J is 0. So if you multiply the value of attribute A times the value of attribute J in the instance I, added up over all instances, and the means are 0, that is going to be just the covariance of 2 attributes, attribute I and attribute J. So what we have is that equation, and again, that must hold for every single attribute at the optimal vector E. So you have not just one of these equations, but D of these equations. Right? So I'm going to write the D of these equations all on top of each other. Right? So I have the sum, J equals 1 to D. I have the covariance of the first attribute with J times EJ, the jth element of my optimal vector E, and that's going to be lambda times E1, the first component of the vector E. Right? What I'm doing is I'm just repeating this equation, but I'm replacing A with numbers from 1 down to D. Okay? And now you look at that, you stare at it for a while, and you realize that what I'm doing here is this is a dot product. Right? What I'm doing is I'm taking a row where each element is the covariance of attribute 1 with attribute J, so a row of covariances, and I'm multiplying it by my dimension, by my vector E. So it's just a dot product between some row of covariances and the vector E. And in fact, it's not just some row, it's the first row of the covariance matrix. It's the covariances of the first attribute with all other attributes. That's my first equation. The second equation is going to be the covariance of the second attribute with all other attributes multiplied by the vector E, and all the way down to vector D. Okay. Now, if you so what you're doing is, and in all cases, I'm multiplying by the same vector E. So really, what I'm doing is I'm taking a covariance matrix and multiplying it by the vector E, just as a sequence of D equations. So if you look at it for a while, you'll see that that is what this system of equations describes. I'm taking a covariance matrix sigma. Every row of it turns into a dot product when you multiply it by your vector E. So that's the dot product between the first row and E. That's the dot product between the last row and E. And what I get back is the first element of E multiplied by lambda, the second element of E multiplied by lambda, all the way down to the last element of E multiplied by lambda. So all in one equation, it gives you that form. It's the covariance matrix times E must be lambda times E. Okay? What does that mean? This means that E must be an eigenvector. Remember, we didn't start by saying that E is an eigenvector. Here we said let's look for any vector E that maximizes the variance. And we did a derivative of the variance, and we found a vector, and it turns out that that vector has the property that when you multiply it by the covariance matrix, it gets longer or shorter, but doesn't change direction. So that vector E must be an eigenvector. So what we've just proved is that the eigenvector is a vector that maximizes the variance in the data. Furthermore, this lambda, the Lagrange multiplier, is an eigenvalue. Okay? Again, we didn't say that lambda was an eigenvalue. It started out just being an undetermined Lagrange multiplier, and it turns out to be the eigenvalue of sigma. So that's pretty cool, right? What we've shown is if you look for the direction of the greatest variance in the data, you are going to find an eigenvector and nothing else.